So now in hidden Markov model, we have already seen a very important problem, which is the Viterbi algorithm. The Viterbi algorithm makes use of the observation and tries to predict the state sequence, right? So in the ARN sequence problem, we have the observations as red ball, green ball, uh, blue ball, and so on, sequence of colors for the balls. And we have to predict the best sequence of ARNs from which such an observation has arrived. A best sequence of ARNs means the most probable sequence. And the most important idea in Viterbi algorithm is to keep track of the paths ending in the same state. Okay, so initially you start from S0, and let's say there is the probability of 0.5 to go to pick up the ball from U1, and then 0.3 for U2, and 0.2 for U3. And then you observe R, okay, the red ball. And then you know the probability of going from U1 to U1 or remaining in U1 with observation as R is 0.03. It is 0.3 into 0.1. Okay. Then U1 to U2 with red observation is 0.08 and so on. We similarly look at the path passing through U2, S0, U2 and U1, S0, U3, U1. So all the paths which are ending in U1, I note their probability. So we'll have to carry out a max operation. Okay, so that is another computational part. And when we carry out the max operation, we find out which path has the highest probability. All these paths are ending in U1. So this path has 0.03 into 0.5. This path has 0.02 into 0.3. This is 0.18 into 0.2. So the accumulated probabilities are 0.015, 0.012, 0.036. So this path will be the winner. And none of the other paths ending in U1 will be advanced any further in future. Okay, and this is due to Markov assumption. So while from S0 we had 3 states, from after the first observation also there will be only 3 states, because all the paths ending in U1 will give rise to only one path. All the paths ending in U2, only one path will remain. Similarly for U3. So again, you will be ending up with only 3 states after the first observation. Then after the first observation, when the second observation comes, again, there will be 3 into 3, 9 paths. Out of them, only 3 will remain. So after every observation, the number of states is only the number of states to be advanced is equal to the total number of states. Okay, so what threatened to be an exponential algorithm reduces to a linear algorithm, linear in the length of the path and quadratic in the number of states. Quadratic because you will have to carry out a max operation for the number of paths, which is equal to the number of states. Okay, so this is how the algorithm, Viterbi algorithm, will proceed. And the key point is the paths which get which no longer advance due to the Markov assumption. The same idea comes to the forward-backward algorithm also. Okay, and the implementation is based on dynamic programming. You will have to implement Viterbi in the lab. Okay, which should cement your understanding of Viterbi. So let's take stock of the fundamental AI concepts that I believe you have been theoretically comfortable, and also quite sound understanding has happened through lab implementation. So A star, I believe everybody is now confident of A star algorithm. Then perceptron, backpropagation, all of you should be confident. In today's lab, SVM should be clear, max margin classifier. After some time, hidden Markov model, Viterbi should become well grounded in your mind. Predicate calculus, prologue, fuzzy logic. These you have not implemented, but I believe you are, you are familiar with the concepts, and we'll see what to do about it with respect to implementation. Okay. So I think to my mind, the course is going on fine with respect to creating a foundation for AI. This is your first exposure to AI. So creating a foundation for AI is happening. Okay, so now let us proceed to probability of observation sequence. Here we had a very interesting situation. No knowledge of meaning, no knowledge of grammar, no knowledge of spelling is required if you have the power of data and probability. That's very remarkable. Okay, we take so much pain to learn a language, the grammar of the language, the spellings, the idioms, proverbs, dictionary. Okay, and it takes an enormous time to acquire a language. The second language learning is faster, but it is proved that the first language interferes with the learning of second language. An example of this can be seen when Indians say, "You will come to my house," no? So this is not there in American English, British English, and French English, Mauritius English, Dutch English. Okay, everywhere you have different variations of English. You have different variations of Hindi in our country. There is Bengali influence, there is Tamil influence, and so on. But this is typical. You will come to my house, no? Okay. The actual English, classical form would be, "You will come to my house, won't you?" Okay. So no such nuances, knowledge of grammar, knowledge of meaning, etc. is required. Just have huge amount of corpus data and compute probability of strings. Okay, and that gives rise to what is called language model. Language model is the foundation of deep learning based NLP, and large language models are expansion of language models. Large because there is a long context. Okay, and everywhere it is probability which is playing its role. Everything is play of probability and data and maximum likelihood estimate. So this is very remarkable that the probability of the correct sentence will come out the highest, and spelling mistake, grammatical mistake, and semantic mistake will be penalized because of probability. So how to compute the probability of an observation sequence? Notice that you can apply the chain rule, probability of O0 into probability of O1 given O0, probability of O2 given O1, and so on. But the thing is that you don't have these probability values in hidden Markov model. In hidden Markov model, all you have is transition probability and observation probability. Okay, so if the underlying machine learning, if the underlying machinery is hidden Markov model, then you have to make use of transition and observation probabilities. Can this be done? Yes, it can be done by a powerful concept called marginalization. For any probability, you can introduce another random variable always, provided that random variable takes all possible values from its own domain. So PO, the probability observation sequence, is sigma PO comma S. S is the random variable for the state. If S takes all possible values of the states, then this formula is valid because of the law of marginalization. So probability O comma S, joint probability is probability of S into probability of O given S. So this can be easily processed by Markov assumption. Probability of S is probability of the state sequence. Probability of O given S is probability of the observation sequence given the state sequence. And probability of state sequence makes use of the Markov assumption. You have probability of S0 into probability of S1 given S0, etc., which is nothing but the transition probability. And probability of the observation sequence given state sequence is probability of observation given the state, again by Markov assumption. And these are nothing but the emission probabilities, the observation probabilities. So we have done this grouping before, probability of S0 into probability of O0 given S0, probability of S1 given S0, and so on. And we have seen that this particular product is probability of S0 to S1, probability of S0 to S1 emitting O0. Okay, so this is the transition probability along with observation, okay, which we have seen before also in the ARN problem. You can take the product of observation probability and transition probability. So this is the way the probability of the observation sequence is obtained, incorporating transition and observation probabilities. Now, the question is how to compute these probabilities, because there is always lurking in the background a threat of exponential computation unless we do the computation cleverly. So we define two very useful quantities called forward probability and backward probability. Let's see the definition of forward probability, Fk, I. Many times the forward probability is also expressed as alpha probability. Okay, alpha, and backward probability is called beta probability. We'll make use of capital Roman letters here and not Greek letters. So define F, I as the probability of being in state Si, having seen the prefix of the observation sequence. So prefix, what is the length of the prefix? The length of the prefix is k plus 1, O0, O1, O2 up to OK. So probability of being in state Si, having seen O0, O1, O2, OK. So Fk, I is the joint probability of the prefix of the observation and state Si. Okay, it's a joint probability with M as the length of the observed sequence. So probability of the observed sequence by this definition becomes probability of O0, O1 up to OM. And after seeing the whole observation sequence, the machine can be in any of the states SP, where P goes from 0 to N plus 1 being the number of states. N. So this should be N plus 1. N plus 1 is the number of states. Okay. So therefore, the probability of the observation sequence is the sum of the forward probability of the whole string, comma P varying over the over all the states. Okay. So this is how forward probability is used to compute observation probability. Okay. Sequence of the observation. So probability of the observation sequence is expressed in terms of forward probability. It's a joint probability. Now this forward probability can be computed efficiently using recursion and Markov assumption. So look at this forward probability Fk, Q, where a prefix of length k plus 1 is seen in the observation sequence prefix and being in the state SQ. So this is probability of O0, O1 up to OK, SQ. Now, what I do is that I isolate OK and shorten the length of the prefix by one symbol. So probability O0, O1, O2 up to OK minus 1, OK, SQ. Now I use marginalization. So marginalization and Markov assumption are invoked all the time in hidden Markov model-based computation. So this becomes probability of O0, O1 up to OK minus 1, the shortened prefix, comma SP, all possible states SP, which the machine can be in, seeing the shortened prefix. OK is already separated and SQ is the original FKQ expression. So this is written as then sigma p equal to 0 to n, this expression, then sigma p 0 to n, probability of O0 up to OK minus 1 SP into probability of OK. So after OK minus 1, I introduce SP, where P varies over all possible states. Then OK is isolated, SQ is the original Q. So here I apply chain rule of probability. So probability of O0 to OK minus 1 SP into OK, comma SQ, conditioned on SP and the shortened prefix. Okay, so now apply Markov assumption that probability of OK, SQ depends only on SP, the previous state, before OK. And probability of OK, SQ given SP, we have a nice notation for it. This probability of SP to SQ emitting OK. Okay, this notation. So we have been able to express Fk, Q as a recursive expression, which is the forward probability of a k minus 1 to p. That means a shorter computation multiplied by probability of SP going to SQ emitting OP over all possible states P. Okay, all possible states P. And SP to SQ emits OK. So we have a recursive expression for FKQ, which will assist in the efficient computation of this forward probability. Now let's deal with backward probability. Backward probability is dependent on suffix. Okay, while forward probability was making use of prefix, backward probability is dependent on suffix. Define Bk, I, the probability of seeing OK to OM. Okay, so from the position K up to the end of the observation sequence. So that's a suffix. Given that the state was Si, so Bki therefore is probability of the suffix given Si. What is the probability of seeing the suffix starting from the state Si? With M as the length of the whole observed sequence. So if that is the definition of the backward probability, then the probability of the observed sequence is the probability of O0 to OM, which is nothing but probability of O0 to OM given S0. S0 is the starting state, which is B0, 0. Okay, so the backward probability has an interesting expression with respect to the whole observation probability. It is just B0, 0. More elegant than the expression in terms of forward probability, which is in terms of a summation and Fm, P. Okay, so does it mean that forward probability will be more or less efficient than backward probability? It turns out that that is not the case. Okay, you make use of dynamic programming Markov assumption, and you have a linear time algorithm for forward probability and backward probability for both. So let's proceed. Then for backward probability also, we have a nice recursive expression. Bk, P is probability of suffix given SP. So again, I isolate OK, OK, which is the front, the head of the suffix. The head of the suffix is isolated. And we introduce all possible states SQ by marginalization and take the summation. So this can be written as summation Q0 to N probability of OK, SQ given SP into probability of a shorter suffix. Okay, so the probability of the shorter suffix is probability of OK plus 1 up to OM. OK, the head is omitted. And conditioning part is OK, SQ, SP. And we note that by Markov assumption, this probability depends only on SP, the state SP. So again, the backward probability is coming out to be Bk plus 1, Q into probability of SP going to SQ emitting OK. Okay, like before, like forward probability. So this is a summation expression involving shorter suffix and the probability of transition from SP to SQ, like forward probability. Okay, forward probability had this expression. So both backward and forward probability has a nice recursive expression. Okay, and you can compute this efficiently in linear time with respect to observation sequence. So just sit down with the derivation and maths. It follows quite systematically, step by step. Now, how does the forward probability work? Okay, here is a small intuitive example. To find the probability of the observation sequence here is I'm illustrating this in terms of language, in terms of NLP. So suppose you have a sentence, people laugh. Now people can be both noun and verb. Laugh also can be noun and verb. I had a good laugh. Here it is a noun. And they laugh heartily, that's a verb. People can be noun and verb both. But the verb sense of people is little rare. This means to populate. Okay, the city was peopled with soldiers. So that's a verb. This hat symbol is the beginning of the sequence. Dot symbol is the sentence ender. So we start with the hat symbol. This is the state. And on epsilon, I mean, observing nothing, we go to the next state, which is either noun or verb for people. And then from noun, from this n, I can again go to noun or verb because laugh can be both noun and verb. And finally, with the dot, I finish looking at the sequence. So we would like to find out the probability of the observation sequence in terms of the state transition probabilities and the observation probabilities. You can also make use of Viterbi algorithm here to get the best possible state sequence, which means the best possible part of speech tag sequence. So the way it will work, okay, we'll not go into lots of details. It's very clear from the slides. We have the transition probability. So transition probability is saying, if we start with in the beginning of the sentence, which is indicated by this hat symbol, the probability of remaining in the hat symbol, that is the beginning of the sentence, is 0. Because then you're looking for the next word. What is the probability of a sentence starting with a noun? Let's say this is 70%. Large number of sentences in English start with a noun. So this is 0.7. What is the probability that the sentence starts with verb? 0.3. We assume that we have only nouns and verbs in the sentence. And then probability of going to the end of the sentence without seeing any word, that probability is 0. Sentences must have some finite length. After the noun, you cannot see the beginning of the sentence again. That's why this probability is 0. After the noun, can you see another noun? That probability is small. It's only 0.2. What is a situation where a noun follows another noun? Cricket, bat, for example. Cricket is noun, bat is also a noun. So there are instances of noun following noun. But verb definitely follows noun. So that's why that probability is 60%. And can a sentence end with noun? Yes, a lot of sentences end with noun. Okay, Ram plays cricket, for example. So that probability is 0.2. What is the probability of going to the beginning of the sentence after seeing a verb? 0. What is the probability of seeing a noun after verb? Quite high, 60%. Plays cricket, for example, is noun following the verb. Verb following verb, small probability, only 20%. Okay, so what is an example of verb following a verb? So is going, for example, you have auxiliary verb and the main verb. And a sentence ending with verb is very likely. Then finally, we have dot. Dot going to a hat. The probability is 100% probability. Why so? Because after dot, a new sentence will begin. Okay, so that's why it is 100% probability. So this kind of transition probability table is created when you have your assignment in the lab, okay, involving hidden Markov model. Make sure you make use of the data given to construct the transition probability table by taking ratios of counts. Then we have another probability table, which is the emission probability table. The probability of seeing epsilon after beginning of the sentence, that is 100%. Okay, you do not see anything after this beginning of the sentence because the assumption is that you do the transition to the next state with epsilon. So from noun state, you cannot see an epsilon, 0. People being a noun, probability is 0.8. Laugh being a noun, 20%. People being a verb is 10%. People laugh being a verb 90%. Okay, that is according to the property of the language and the rest of the rows. So an inefficient computation will be the probability of people laugh. If you want to compute, you can introduce the transition and emission probability by marginalization. Okay, PO comma S. S is coming with summation. And then it can be computed by taking product of SI to SI plus 1 on OJ for all possible I and J. But that will be a very inefficient computation. It will be exponential. So what you can do is that you can make use of Markov assumption and the recursive expression for forward and backward probability. So I have this starting state hat. On epsilon, it goes to noun or verb. On seeing people, it goes to noun or verb. This V goes to noun or verb. And after seeing laugh, this N goes to final state dot, V goes to final state, this N, this V, all of them go to final state. Okay, so here you can make use of Viterbi-like idea. Okay, and the states that the paths that end in the same state, you deal with it efficiently in terms of Markov assumption. So the calculations are given here. You can follow that. So for path 1, we have probability of path 1 is this accumulated probability. Okay, then path 2, you have the accumulated probability, path 3, path 4, and so on. But this way of accumulating probabilities will require exponential computation. Because you see everywhere you have states giving rise to equal number of states. So instead of that, if you make use of the recursive expression, the forward probability, okay, if you make use of the forward probability, then notice that each of these forward probability computation can make use of partial forward probability computation. That's dynamic programming. Okay, so all F12 can make use of F11, F21 can make use of F11, and so on. So you don't have to recompute everything. You can make use of the previous done computation. And when you do so, you have a much faster way of computation. So the tree, each path has 5 multiplication plus 1 addition. There are 4 paths in the tree, therefore total number of 20 multiplication and 3 additions. Whereas if you work with forward probabilities and the trellis, then F11 1 multiplication, F12 1 multiplication, F21 is F11 into 1 multiplication plus F12 into 1 multiplication, 4 multiplication plus 1. Addition, similarly for F22 and F31, 4 multiplication and 1 addition each. So total of 14 multiplication and 3 additions, as opposed to 20 multiplication and 3 additions. And as the observation sequence becomes longer and longer, this kind of gap between trellis-based computation and tree-based computation becomes much more stark, okay, much more dramatic. So I show the complexity of forward algorithm, okay, and that complexity is S, the number of states, plus 2 into S square into observation length minus 1 plus 2 into S. So this is linear in observation length and quadratic in the number of states, just like Viterbi. Okay, so what is very interesting is that Viterbi forward and backward are actually the same algorithm. Okay, in one case you take the max. Viterbi makes use of max operation, and forward and backward algorithm make use of addition operation. Okay, so addition and max are the two operations which separate Viterbi from forward or backward algorithm. Okay, so these things you must see from the slides as well as research paper, books, etc., and make sure that complexity calculations are clear in your mind. It's a very beautiful application of the Markov assumption. Okay, and the key point to remember is max versus addition. So forward algorithm has this order S square O complexity. Backward probability also you can similarly deal with and express PO in terms of both backward and forward probability. The probability of the observation sequence you can expressed in terms of both forward and backward probability. Now, I would like to, after this, the main topic is Baum-Welch algorithm, where you learn the transition and observation probabilities. But that requires some essential maths. So let me just start with that and come back after a decision tree and a regression discussion. Okay. So maximum likelihood estimate you have been exposed to very well in the previous course on data interpretation. So let's explain this with a very familiar example. A coin is tossed 100 times, head appears 40 times. The probability of head is 0.4, which is a parameter for the coin. Why is the probability of head 0.4? What is the basis of this computation by means of ratio? Because of the maximum likelihood principle. Okay, so the hidden parameter here is the probability of head that controls the probability of the observation. So this is the way we derive the expression for pH. We construct the maximum likelihood expression. First, construct the likelihood expression. So if there have been k heads, there must be n minus k tails. So the likelihood or the probability of the observation sequence is p to the power k into 1 minus p to the power n minus k. So it is difficult to work with exponentiation. So take log likelihood. So log likelihood is k log p plus n minus k into log 1 minus p. Now differentiate log likelihood with respect to p, the parameter I am interested in. When you do so, then k by p minus n minus k by 1 minus p comes out. We equate this to 0. That gives me p equal to k by n. So that is the foundation for taking ratio of counts for finding out the probability. Okay, it is because we want to maximize the likelihood, and the likelihood is a function of the probability of the parameters. Now we come to expectation maximization, which is another very powerful idea. And I think I have dealt with this pretty well in a book that I wrote on machine translation. So the discussion is from there. So there are two situations. The first situation is throw off a single coin. In case of single coin, the discussion follows typically the likelihood expression, setting up the likelihood expression and maximizing this. Here we introduce a slight twist in the discussion, okay, namely indicator variable. The parameter is the probability P of getting heads in a single toss. Let n be the number of tosses, then the observation X and the data for observation likelihood D respectively are X is X1, X2, X3 up to Xn, where these Xi's are what are called indicator variables. Okay, so these Xi's are 1 or 0. And P is between 0 and 1. There is a reason why we are not working with the total number of heads and total number of tails. Okay, it gives me an instrument to deal with a more complex situation where two coins are tossed. Okay, and the observation sequence is again head and tail. Only point is that the observations are coming from two coins, and we do not know what is the which is the coin which is chosen. And there is a probability associated with choosing one of the two coins. So indicator variable is introduced. Now same likelihood expression, which was p to the power k 1 minus p to the power n minus k, can be written as p to the power xi into 1 minus p to the power 1 minus xi, I equal to 1 to n, which is exactly equivalent to p to the power k into 1 minus p to the power n minus k. Okay, so when xi is 1, 1 minus p to the power 1 minus xi becomes 1. When this becomes p, and when xi is 0, then p to the power xi disappears, and we have 1 minus p to the power 1. And when you take this product, it is equal to p to the power number of heads, 1 minus p to the power number of tails. So indicator variables is equivalent to working with the count. So this is again a very common idea in combinatorics. Okay, a very common idea in combinatorics, where you can always replace counts, okay, with the summation of indicator variables. Indicator variables takes one or zero. Okay, so it's a very powerful and nice idea from combinatorics, where counting is in terms of addition of variables. Okay, so we have replaced the counts of heads and tails with indicator variables. So in case of single coin, say we have again have the situation of this likelihood expression. This is the likelihood expression. Okay, we take the log and we find out that the probability of head comes out to be I equal to 1 to n xi divided by n. And I equal to 1 to n xi is exactly equal to count of the number of heads. Because xi takes value 1 or 0. 1 for head, 0 for tail. Okay. So using the indicator variable also, we have been able to get this expression. Now we come to the expectation maximization. Suppose two coins are thrown. Okay. And we randomly choose one of the two coins. There are now three parameters: probabilities P1 and P2 of heads of the two coins, and the probability P of choosing the first coin. Automatically 1 minus P is the probability of choosing the second coin. Okay. So n tosses an observation of heads and tails, only we do not know which observation comes from which coin. So if you're wondering why all this discussion is towards Baum-Welch algorithm for learning the parameters of the hidden Markov model, the transition probability and the observation probability. The indicator variable Zi is introduced to capture the coin choice. Zi equal to 1 if coin 1 is chosen, otherwise 0. This variable is hidden. That is, we do not know its values. However, without it, the likelihood expression would have been very, very cumbersome. So now we can set up the data likelihood. The data likelihood is the probability of the observation. Okay, and the probability of the observation is controlled by these three parameters: P1, the probability of head from the first coin; P2, the probability of head from the second coin; P, the probability of choosing the first coin. So this is P theta x, where theta is P, P1, and P2. We marginalize this on the indicator variable Z, where Z is a hidden variable as to which coin is chosen. So the data likelihood D is now sigma over all possible Z, P theta x comma Z, where x is the sequence x1, x2 up to xn, takes value 1 if the observation is head, otherwise 0. And Z equal to Z1, Z2 up to Zn takes value 1 if the first coin is chosen. Okay, so if we get a head from the first coin, then x1 is 1, Z1 is also 1. If you get probability, if the head is coming from the second coin, then x1 is 1, Z1 is 0. So now P theta x comma Z, you can show is this expression. This expression, though looks a bit complex, is not so. If you think of it this way, I equal to 1 to n, this is for the indicator variables. The indicator variable is for each position. So first expression P1 to the power xi into 1 minus P1 to the power 1 minus xi is for the situation involving first coin. Okay, and since the first coin is chosen, it is a joint probability of P into P1 to the power xi into 1 minus P1 to the power 1 minus xi. The whole thing is raised to the power Zi. Where Zi is the indicator variable, Zi is equal to 1 means that this expression will be involved because the observation is coming from the first coin. The second expression is 1 minus P into an expression involving P2, exactly like P1. Only it is raised to the power 1 minus Zi. So this part of the expression is for the second coin. This part of the expression is for the first coin. And within the expression, the phenomenon is if head is obtained, P1 to the power xi. If tail is obtained, 1 minus P1 to the power 1 minus xi. So xi is 1 or 0, and P1, P2 are between 0 and 1. Okay. So then we make use of Jensen equality here, making use of the convexity of the expression. And we observe that log of I equal to 1 to k lambda I xi is greater than or equal to. The log can move inside. Okay. I equal to 1 to k lambda I log I, where sigma lambda I is equal to 1. This is Jensen's equality. So once you do that, the log likelihood of the data, okay, which is log p theta x and log of sigma z p theta x comma z, by making use of Jensen's equality and introducing appropriate lambda z, we obtain this log likelihood expression is greater than or equal to sigma z lambda z log of p theta xz by lambda z. Okay, because you have multiplied by lambda z and you have to divide by lambda z to maintain equality. So after a number of intricate mathematical steps, okay, there is a very nice treatment of this in Sean Borman, SCAN, Sean Borman. I'll send it on Teams. Okay, very nice mathematical treatment here. The log likelihood of the data or the observation comes out to be expectation of log p theta x comma z, where e is the expectation function. Note that the expectation is conditional on x. X is the observation. So once you do that, okay, all these are like you can say the lines in a poetry, right? Okay, they're very elegantly follow from the previous step. Okay, all laws of probability are being used and expectation. So when you keep doing so, then you come to this expression and taking the partial derivative of this expectation expression, we find the probability of choosing the first coin comes out to be expectation of Zi given Xi, I equal to 1 to n divided by n. Expected number of times the first coin is chosen. Okay. P1 also is very intuitive. Expected number of times the first coin is chosen multiplied by Xi, where Xi is 1 for head, divided by expected number of times the first coin is chosen. So this ratio is expected number of times head is seen from the first coin divided by expected number of times the first coin is chosen. P2 is m minus this quantity n minus this quantity, which is expected number of times the head is coming from second coin divided by expected number of times the second coin is chosen. So all these follow very neatly from the probabilistic treatment of the expression. If possible, take a look at this derivation from this book here. This book should be available. And the chapter 2 deals with this expectation maximization. And this expectation maximization is used for Baum-Welch algorithm and also for creating alignment between image and text, between two images, between two parallel texts. Everywhere alignment is involved, this expectation maximization is at play. Okay, this happened in 1980s, 90s, and it was a very important milestone in the history of AI. All alignment depends on expectation maximization, and alignment happens between the two eyes, for example. Okay, to give me a sense of depth, for example. Okay, so these are nice, very nice topics. Take a look at them, and we'll come back to them apart from other